actually my goal is to create autonomous robots so that there's no need for a human being anymore. No, I'm just joking. Some of you may take it seriously and go purchase a gun. So one thing I don't know whether I told you, but a few years from now, there won't be lectures like this anymore. And so we're going to be obsolete because of AI. You've seen all those, maybe you have not, but if you go to some of the best groups like Coursera or Udemy, you'll see some beautiful lectures that we can't reproduce because they put so much into the graphics, right? So when people have access to that, I don't think they're going to listen to the traditional lecture anymore. So I'm sorry, I didn't mean to frighten you. But that's coming. So, so I don't know how much, well, you're ahead of me actually. You know ROS 2, and I'm going to learn ROS 2 in the summer. But when I learn it, I have to learn it so as to be able to teach it, which is the difference between just knowing it and knowing it to be able to teach it. Because students will ask the strangest questions, legitimate questions, and you have to have an answer for it. So I just quickly go through this, and as I was saying before we formally got started, I posted some files so that they are available as a backup, so that between now and Saturday, if some of the things I show you, you can't get it to work, you can go back and follow the instructions. So those are precise instructions. And the whole idea is to be able to launch ROS and move a robot in it, look at some sensor data, and also try to command the robot. So that's the complete loop, right? Because we get data, we process it, and then we do something to the robot. We ask the robot to do something. So hopefully we'll get through all of that before 1 o'clock. But feel free to stop me and ask. I don't want to leave you behind. Okay, so you know, we are on the verge of moving over to ROS 2, and then it has already started with Ubuntu 22.04. I believe 24 is already out, if I'm not mistaken. So the thing with these Ubuntu versions is that there's something attached to it called, you know, long-term support, LTS. So the support is going to be shortly withdrawn because the open source community moves on and works on 22.04 and 24 and so on. It's only one group of people. And so at that point, you use it at your own risk. You use older versions at your own risk. And the same thing with ROS. ROS and Ubuntu are kind of hand in hand. So Noetic has already been replaced by a ROS 2 version. In this version, there is a bridge available to ROS 1 so that you can still port stuff over, all your old stuff that you spend hours creating. But after that, there'll be little support for that. Okay, so I'm using MATLAB 2023A. There's already 2024A released, but I always like to hang back, you know, because new versions always have glitches in them, even after release. So typically I wait for a year. All right, so let's get started. So by the way, MATLAB has the same role as Python does. MATLAB and Python are like cousins. MATLAB you have to pay hundreds of dollars for the license. Python is free. But because of having to pay for the license, you get immediate support. You can file a ticket, and by tomorrow they give you a 24-hour period before they respond. But after that, they are with you every day till the problem is solved. Python, you know, you have to solve the problem on your own. There's nobody who's going to help you except by out of the goodness of their heart. I'm going to skip some of this because, you know, we're already in ROS 2, so there's no point in spending time on this. So the architecture is kind of important because when you launch a program, it basically leverages the architecture, so we should know something about it. So the ROS master, as you know, does not exist anymore in ROS 2. In ROS 1, it does. So the ROS master, so you have different nodes, and these nodes can be thought of as functional units. You know, it sort of implements something, a task. It could be like face recognition. It could be something that just drives the robot, right? Or it could be something that processes LiDAR data. So basically, you break up the task into smaller tasks, and then you assign them to nodes. So the advantage of assigning them to nodes is that when you run it under Ubuntu, so Ubuntu is a multitasking system, right? So multitasking has to be understood in its proper context, you know. No human being can multitask, despite the fact that many boast that they can do. What they're saying is, I can temporarily suspend this and do this. You can't play tennis and cricket at the same time. If you can, I will prove that you can't. You just have to pick up the pace a little bit of the balls being bowled to you and the tennis balls that are being hit at you across the net. So multitasking means that you can do two tasks at the same time, and that's just not possible. So what the computer does and what human beings also do, like many of us are capable of doing it, is we can go through multiple tasks and come back to the first one rapidly. So when you distribute the task in nodes like this, Ubuntu is capable of running node 1, node 2, node n, and then back again. And so fast that it appears as if it's doing it simultaneously. Now, we can go a step further. Many of the modern computers have 32 and more cores in them. So you can say, I want ROS node 1 to run on the first core. So yes, then it's running all the time by itself, right? And similarly, you can assign ROS node 2 to a different core. And therefore, you get this parallelism. But before you do that, typically, one processor is kind of cycling through all the nodes at a high speed. Now, there's also this beautiful arrangement that you can do. Maybe you feel that ROS node 2 is doing a lot of work, so you need to give it more attention than the other nodes. So it is possible to dictate the frequency or the block of time that you allocate to ROS node 2 versus ROS node 1. So that requires creativity. You have to know your nodes. Image processing typically takes a long time, right? But then some sensors might be quite slow in their data coming in because the nature of the sensor, it's too expensive, right? GPS is like, it used to be 1 per second at the very beginning. It's faster now, but it's not as fast as other sensory devices. So maybe there's no point in hurrying it up because you're only getting an input data once every, a long block of time. So at that point, you need an architect because you can't just say, okay, I'll give this to this, then this to this. You have to know how fast your different nodes are running at. It requires like a surgeon at the computer level to be able to do it. But other than that, Ubuntu is just cycling through all the nodes. And you call that multitasking. Okay, so over here you see why you would want to do that. So for example, here's the computer on the robot and the remote computer. So typically you have at least two, but for an example, you could have one in Japan across the world because the communication is TCP/IP based. So if you have a powerful supercomputer somewhere and they give you permission to use it, you can include them in your robotics solution loop. So you can spread the task around all over the world. So two computers, we have, by the way, we go to robotics competitions regularly, and we've gone as high as 3 computers on the robot itself, plus a remote, because we were doing image processing of lane lines. So lane lines, paint on grass creates approximate lane lines. So it's a very difficult job in image processing. It's not like lane lines on a tar surface. On grass, it becomes a much more difficult thing. So we had 3 computers. One was exclusively doing image processing while the robot was moving. And we were only moving at a maximum of 5 miles per hour. So imagine at highway speeds, even that might not be enough. So here's the camera node, and its only job is to get the image from the camera and then do some low-level massaging operations, some noise removal or whatever they do in image processing at the lowest level. That's it. And then the image processing node does this heavy lifting. So how does this communicate with that? It does so using topics. So this camera node publishes to this topic. Okay? It's like putting something on a bulletin board. So when you put something on a bulletin board, anybody can access it, right? Anybody who wants it can go and look at it. So that's what a topic is. It's a message published on a bulletin board. So the image processing node, so just like this camera node publishes it, the image processing node subscribes to that same piece of information. Now they have features like, is this fresh? Is this new? Because if it's not a new image, why would you even bother? Because you already processed it, right? So you have those little features, you can check for whether the information is new or not. And also you have an image display node on the remote laptop because you want to see what the robot sees sometimes, because for debugging purposes, you don't want to see through the robot's computer, because then you have to be walking behind it. So you have a image display node, and that's also subscribing to the image. So you have to understand this concept of many publishers and many subscribers. So you have a topic with a message structure. Message structure is defined by this, whatever is contained in this, right? Because different data have different formats. So essentially, you put it on the bulletin board, you have many subscribers, whoever wants it can take it, and that's one form of communication. All right, so the other form of communication, which we rarely use, is known as services. So as I said, I'm not in a position right now to tell you what got left out in ROS 2 and what got preserved, because I don't know enough about ROS 2. I know the ROS master is no longer needed. So what is the ROS master doing, by the way? The ROS master is basically like a cop. In other words, how will there be an awareness of all the nodes, right? So somebody has to keep track of that, like a ledger. So basically, the cop, ROS master, the policeman, keeps track of all of that. But no data passes through the ROS master. So essentially, it has lookup tables, so that every node knows where, what the address of the other nodes are, and that's its only job. So this is, you can see the difference here. The service works by, it's synchronous communication. The previous mode was asynchronous, meaning that you put it on the bulletin board, it's up to whoever wants it to go get it. It's asynchronous, right? Here, it's like somebody taps you on the shoulder and says, give me a new image frame. So this is the tap, the request. So this is more immediate. You have a better control of time. Because remember, if you get an image 5 seconds in the past, well, depending upon how fast your robot is moving. If your robot is not moving, 5 seconds in the past would be great, right? But if your robot is going at 100 miles per hour, then 5 seconds in the past, the image is no good. You can throw it away. So essentially, this is more immediate because you send a request and you get a response here back to the image processing node. So real-time systems need that. You can't be using data from the past. So this is more immediate. Okay, so that's the difference between topics and services. So this, you probably know from your ROS 2 discussion, the whole idea is that the ROS architecture enables you to distribute the tasks, right, between different nodes, and so it gives you the ability to architect the whole process for high speed. But also, there are many algorithms that you wouldn't want to be diverted from your main task. You want to get the robot moving and picking up lane lines and so on. You don't want to be writing lane recognition algorithms, just to get the robot to recognize lanes, right? Because that is a lower level task for you. You have a higher level task. So many of the common algorithms are already available as ROS packages, and you can co-opt them. So that is the beauty of the libraries they have. So that's known as abstraction. So abstraction is where you push yourself back. The user pushes away from the details. So for instance, you don't have to know how many motors are in this vehicle or how to drive it. Speaking of which, all robots are driven by a pair of numbers. V, which is the forward velocity, and omega, which is the turn rate in radians per second. So forward velocity in meters per second and turn rate in radians per second. Now, the robot may have 4 motors or 2 motors, but you don't really care, because whatever node is responsible for driving the robot, it takes your V omega and distributes it to however many motors you have. So that's called abstraction, in the sense that you don't need to know the details. It is, in the old days, like, the first time they designed a printer driver. In the absence of a printer driver, you would have to go in and say, okay, how does this printer work and what am I supposed to do? What voltages am I supposed to feed it, right? That's way, way back. 50 years ago, we were actually doing that. We had to figure out, okay, how do I convert my document and to voltages that, make the printer move? And so all these drivers, they basically said, everything is abstracted, go back, you don't need to be here, just send this in this way and it'll work. So that's the whole idea of this concept of packages. Okay, so you have C++. So if you really wanted speed, C++ is the way to go. but as you know, C, C++ is a very hard language to work with unless you have a lot of experience. It's slow development in C, C++. And nowadays, what has happened is people have figured out, for example, how to convert MATLAB code into reasonably efficient C, C++ code. So they have compilers that once you finish developing the algorithm, it is converted to C, C++ code as the final step when you're ready to deploy the algorithm. So C, C++ is actually fading. If you look at some of the surveys, you'll find that C, C++ is not listed as the #1 algorithm in many surveys. It's typically Python. MATLAB does not get the nod because it's expensive, but MATLAB does exactly what Python is capable of doing and more, because they have an army of people who are paid to, develop new versions and new functions and so on. So I, for one, will never give up MATLAB. Some people say Simulink is a better way to go. I don't know whether you know, but Simulink is like a cousin of MATLAB. So Simulink is like a graphical way of describing, a program or an algorithm. We are about to switch to Simulink also because one of my colleagues uses it regularly. It's a more natural way to think of a flowchart. A flowchart is not normal. It's not normal to take a flowchart and write lines of code with it, But Simulink already has loops and everything, and that's the way the younger generation sees an algorithm. So we're going to try Simulink because one of my colleagues has convinced me that that's the way to go this summer. Okay. So both MATLAB and Python are equally slow or equally fast. How you want to look at it? C, C++ is going to be much faster, but the development is going to be slow. You're going to spend many more hours developing the algorithm, but it will run very fast compared to MATLAB and Python. I already mentioned this, ROS provides the functionality for common robot operation tasks like motion control, scene or sensor perception, mapping, path planning, and many, many more actually. So, in ROS 1 you have several tools built in. Well, actually, I should take that back. So Gazebo is an open source movement that started by being in bed with ROS, but later they were separated. So now they have their own open source movement, Gazebo. I think the idea was that ROS wanted them to not depend so much on them, ROS, but also give other simulators a chance. Gazebo is a simulator. They wanted other simulators to get a chance. It's just like all the auto companies in Detroit. They had their own parts departments. Visteon was a very big part supplier for Ford. And at some point they said, okay, they sold them off. So that you know what happens when you have a not a healthy, but a comfortable relationship, you start getting dependent and you're not that good anymore. You don't innovate. So all the auto companies, it's almost as if they had one mind. They got rid of their own private parts makers. And so they will buy parts from anybody across the world now. And Visteon has to go and sell parts to all other auto companies. So that they determine it's a more healthy relationship because then people are not that complacent. Because if you have a ready-made buyer, then you're not going to be trying to do new stuff or reducing costs because you're going to get food on the table no matter what. So they broke that link. So this is open source movement. So no money is involved. But Gazebo was disconnected. It's a separate thing. But it's still the preferred simulator, but other simulators also work. There's one known as Carla. You can Google it and take a look. It's a full regular car simulator. And it's amazing how they create roads with water on it, to change the conditions of traction and so on. So it's much more advanced than Gazebo, but you should go take a look at it. That's an option if you want a different simulator. So RViz, I'll walk you through RViz. So RViz and Gazebo are two different things. Gazebo is a simulator, right? RViz is not a simulator, though sometimes when you look at RViz, you'll say, oh, that's another simulator. It's not. RViz is basically a spy spying on Gazebo. So when a robot is moving in Gazebo, RViz can get all the sensor data and can give you plots of it, etc., etc. So RViz, it's a spy. Literally, that's the best way to look at it. It's spying on the robot in Gazebo, and it's grabbing all the information, the sensors, and the commands you give to it to drive it, and it's displaying them in the form of nice plots. Gazebo does not do plotting, so you need RViz to, close the deal. Okay, RQT graph is another thing that we probably won't use much in this course, but you can take a look at it because it's a nice example. So this is one of our projects. We build autonomous robots, and we're also working on self-driving cars now. Let me first set a scene for you. So I already talked to you about nodes, right? Sometimes you may have 37 nodes in your system, and when you're trying to debug, you have to have tools that helps you get to the bottom of the problem. So this is a pictorial view, RQT graph. It's a pictorial view of all the nodes and the connectivity. If one connectivity is broken, it means you're not subscribing to a topic, for instance. So you may ask yourself, why is the robot not moving? So maybe you missed subscribing to a topic, right? So it will show that, yeah, the topic is there, but this particular module is not subscribing to it. Module meaning node. So it's a way of helping you debug a problem. So you can see this is quite complicated. This is not our robot. I just got this from the internet, but ours is equally, complicated. So here, what you see is gazebo. So that's a simulation environment, not the real robot. And then this is Orbis on the left. Okay, and this robot, as it moves, it's going to pick up obstacles, right? And the Orbis is going to show you the robot's view, right? A bird's eye view, and it's also going to show you the presence of the lane lines and the obstacles. Now we may have to play this twice to get our bearings, but let me first play it the first time. You have to, because of the resolution of the projector, you have to look hard. So this is the point of view here, and I don't know, can you see that the robot is also moving here right here? And it's picking up elements that it's putting on a map. The idea is the robot has to go to that red dot there. I'll play it again once you have an idea of what's going on here. So notice, it is not a very well written algorithm at this stage. It is swaying too much left to right because you get seasickness in an actual car, if you are doing that. So this is an early development version of our robot. So we kind of take our human skills for granted, unless we had a couple of drinks. This is not how we would walk down the hallway, but we routinely take our own skills for granted. It's very hard to get a computer to act like a human being, even in a limited way. So what you're seeing is overcorrection. It sees a lane line, and instead of gently correcting like we would when we're driving, unless there's an emergency, right? It's kind of going like this. And so it's seeing the other lane line. So it's bouncing back. The control system is underdamped. So it should be actually, quietened down a little bit. So let's play it again. So what you see is two views. You see the point of view of the robot, and then you see the bird's eye view, and then over here is the gazebo, scene. So let's play it again. The robot is starting out here, the dark shadow there. See overcompensation again, and then it sees the barrel, and it's going to freak out and almost, look at the main line or cross it, and then there is a cement barrier there, and the gap is big enough, but again, it swings to the right and then swings to the left. And then it finally makes it to the red dot, goes the wrong way, and now finds the better gap. So those kind of decisions human beings routinely make without any problem. It's very hard to get a computer to replicate that. So that's the sum total of the power of ROS, Gazebo, and all the simulation tools. I don't know about you, but you never build an actual product, engineering product these days without going through a simulator. It's just a waste of time and money. Because once you have a model of a robot, then you can eliminate so many possibilities that if you actually built them and said, oh, what a crazy idea, you would have spent hours and you would also spend a lot of money. So there's no engineering company in the world that immediately goes and builds the product, because there are too many options. And you don't just pick the first option that you like, right? Because that might not be the best option overall. So that's why simulators are there. they've always been there, but now they're so powerful because computers are so powerful. So pretty much our students who work on the autonomous vehicle team. So by the way, we start the project in September, and the competition is only in May. And so by about November, it gets too cold in Detroit to go outside. There's snow and it's bitterly cold. There was a stretch in January, where the maximum temperature was minus 16 degrees centigrade, the maximum. The minimum was worse than that, and that was there for about 10 days in January. So you can't go outside. So essentially the simulator, and we have a small indoor area where you can run a robot, but it's not very big. You can test out ideas, you can develop your algorithm, and then in March it gets warmer, and that's when they go out and hopefully they've got the simulation behind them so that they can actually test the vehicle at that point. It's cold even in March and April, by the way, but the snow has sort of disappeared. Okay, so there is a bunch of stuff that if you're interested in. All this represents MATLAB documentation that you may or may not be interested in. Okay, so now we're going to set up for the main experiment. I want you to try something in ROS where you can drive a robot in a circle. So this is the first program I get my students to do, because actually there's a lot of stuff you can learn from this very simple program, driving a robot in a circle. Here's how it works. So we are going to use a differentially steered vehicle. So the regular automobile is not a differentially steered vehicle. A regular automobile has what is known as an Ackerman steering, Ackerman. So Ackerman is the name of a person, and probably he has the patent for the original car. Okay. On Saturday you'll see what the Ackerman architecture is, right? But typically the Ackerman architecture requires you to drive through a curve in order to face this way, right? But there are robots that are capable of spinning in place so that without driving forward, I can be facing this way. So much easier to park, right? If you can do that compared to a regular car. Many of us struggle with parallel parking, particularly in places like India and Europe where there's not that much room. So essentially, the mobility of a robot can be much better than a regular car. So a differentially steered vehicle is one which has two drive wheels, okay, and one wheel that is non-driven. So the non-driven wheel is typically like a caster wheel. We don't have any caster chairs here, but you know what I mean? Like there's one wheel that kind of flops around. It's passive. If the way you push the wheelchairs, if you push the wheelchair in a certain way, the caster wheel will align itself with your desires, right? Now, typically differentially steered vehicles have two driven wheels. So if you drive both wheels at the same velocity, it'll go straight. The caster wheels will fall into place, right? If you drive both of the wheels at the same speed in the reverse direction, it's going to go backwards. But if you drive the right wheel faster than the left wheel, it's going to swivel left. And if you drive the left wheel faster, the right wheel is going to swivel right. So that's how a differentially steered vehicle works. If you stop the left wheel and only drive the right wheel, it will pivot around the left wheel. So unlike the Ackerman architecture, a differentially steered vehicle has the ability to kind of face left without moving forward. So we're going to run a simple experiment. We're going to, so this theory will come on Saturday. So right now you have to take it from me that if I drive a differentially steered vehicle, it's going to be the Turtlebot 3 in our case. I'll show it to you in a second. If I take the Turtlebot 3 and give it a forward velocity of v and turn rate of omega, then it moves in a circle whose radius is the ratio of v by omega. And the units are fine because v is meters per second, omega is radians per second. Radius is not a unit, right? So you get meters. So if I use a velocity of 0.4 meters per second and I use an omega of 0.2 radians per second, I should get a radius of 2 meters. Okay? Now, what if I double both v and omega? Well, you will get the same radius, right? Can I triple it? Can I make it like 1,000 miles an hour? That's where you run into the limitations of the robot. In theory, this is true, but you can't use like 1,000 miles per hour because the robot doesn't have the ability to go at that speed. So the Turtlebot 3 happens to have a limitation in speed of 0.22 meters per second. It's quite a slow robot. So it's only like a fifth of a meter per second. Okay? Therefore, you're going to have to work backwards. If I want a radius, right, you first got to say pick the V, and then you'll have to pick the omega. Now, omega also has its limits, but typically it's easier to do this exercise by setting V and finding omega, rather than setting omega and finding that the V is beyond its limits, or whatever. So you typically set V, and then you find omega to satisfy a given R. So you'll see that we can get different radii if I just change the code in the program. So you're going to work with me, and the code is already uploaded, the MATLAB file. It's called driveincircle.n. So here I was just explaining that you can go on a circle. Now you're saying, what is the point of going in a circle? Now I don't have to go on a full circle, right? What if I change V and omega after I've done like 1/10 of the circle? So then I get a different circle, right? So can you imagine that if I have a very complicated path, I should really be able to trace that by a strategy of changing V and omega? Quite frequently. I don't even have to go through 1/10 of a circle. I can go through 1/100th of a circle. And then keep changing the radius of the circle so that I get a very fine path. So that's possible, as you'll see. That's called path planning, right? We can do it. So that is why the circle program is not just to do circles. It's really to string circles together so that you get very complicated, sophisticated paths. Okay, so I think we're ready to launch Ubuntu. I'm going to wait for you to come along with me, because this is an interactive exercise. This one. Introduction to ROS, demo, roadmap, part 1, I think? Yeah, there it is.
Meanwhile, can you please explain the difference between topics and services?
Yeah. So topics is asynchronous. That means any node that is publishing. So all nodes don't have to publish, right? Because a face recognition node, well, I take that back. The face recognition node will publish the results of the face recognition. But there might be nodes that are just doing some processing, right? So it's looking for data, so it's a subscriber. Okay? So there has to be a publisher that publishes the information on a bulletin board that others might want. So here you see that the camera node is publishing, there might be some low-level processing done in the camera node. In fact, there almost certainly is these days. For instance, the image can be color, RGB, and maybe you don't have the processing resources to work with a color image, you want a black and white image. So there is some conversion from black and white to, RGB to black and white, and then it publishes the result here. Now this node, right, it doesn't even care about the rate of the publishing. At some point it's ready to do the first processing job. And so it subscribes to the message, and then it starts working on that frame of data. So essentially everything is asynchronous. There is nobody saying, give me a new image or give me a new face recognition results, right? So there is more synchronicity. When somebody says, give me something, then you're coordinated with this person. That's happening here, because here is a tap on the back. So you have a better control of time. In some real-time applications, you may want to get something right now, not just go and look at the bulletin board and find out what is the latest frame of data. Yeah. So this is a document you want to have open. So has everybody launched Ubuntu? As you may know from your ROS2 session, Ubuntu looks much better than what the screen is saying. This is an old projector, and so we're not getting the resolution. So typically you can't do this kind of work unless you have an extended display, sometimes 2 extended displays. I've seen people with 60-inch displays right next to the computer. So then you can just share it and put a ROS screen, gazebo, MATLAB code, C++ if you're doing, you can put everything on a 60-inch screen. without having to, give it attention or not, or move it off, or minimize it, etc. Is everyone on Ubuntu? No? It's not running? Okay, well, it's time, We have time. So I'll wait. So this is the beauty of VMware. So VMware, let me tell you a little bit while you're firing up Ubuntu, right? I skipped all that, it was on the slide. So VMware allows you to have a fake operating system sitting on top of the real operating system. So for instance, I have Mac OS, but I also have Ubuntu running within VMware. So what do you think is the downside? So the downside is that because you have two layers, a real operating system and a fake operating system, it's going to be slower than a native installation of Ubuntu. A native installation of Ubuntu would be like, I throw out the Mac and just install Ubuntu. But I would never do that because I paid $5,000 for this Mac computer. I'm not going to replace it with Ubuntu. So this gives me a chance to use Ubuntu through VMware. It's a fake operating system, you got it? The beauty is, if I damage that Ubuntu image, right? Let's say I've worked like 2 years, I've created all these fancy programs. If I have a backup of that image, and I crash the original and it's gone, the backup is called a clone, by the way. VMware calls it a clone. So I can put back the clone. So for the clone to be useful, you got to back up frequently, right? When was the first time you backed up your software? After the first disaster. Nobody does it till you have that first disaster where you lose your entire life. I've had a few experiences like that. After that, now I back up every week, sometimes every day. Because before you go to sleep, you just plug it in and it backs up. So if you don't value the hours of effort you put in, then don't back up. But this image can be copied so that when you're trying something new, right, you create a copy because you don't know what's going to happen. And if you crash the system, you can restore it to the previous point. So that's the beauty of a virtual system, but it slows down the whole system. Now, that's not to say you don't back up if you have a native Ubuntu. Anybody who is a serious programmer should be backing up their work. And in fact, the cloud allows you to back up, for very little money. Google gives you, you can buy space and you can put your programs there, at least the programs, not necessarily the whole image, but at least, park your programs there so that you can bring them back. And then you have GitHub and all those, right? GitHub is cloud space basically. You can copy your programs there. Okay, where are we right now? Fine. Huh? Okay. All right, now, so I'm in the home directory. How do I know I'm in the home directory? Because it has my initials there, but if you don't, you do CD with that tilde, it's called a tilde, and that's where I am. That's the home directory. Is that okay? So every user in Ubuntu will have the home directory. So an Ubuntu installation can have many users. You can't see the other users' files, by the way. When you say CD tilde, it'll only take you to your own home directory. And this is like in the old days, right? Windows, you could see music, pictures. You get it? This is your user directory. This is where you work. So at least you can back up this directory. Forget the installation. You can always redo the installation of Ubuntu. But you have all your files if you back up this directory. Well, you don't have to back up music and all that. Backup, in my case, I have the Turtlebot directory here. I'll show you. CD. So, but by the way, for you, it's probably called Catkin. Blesson will clarify. But for me, it is Turtlebot 3_WS because I like my robots to be in separate workspaces. Catkin workspace is common to everything you do. I don't like that. I like to put my different robots in different places, different projects in different workspaces. So all of them should have this _WS to remind ourselves that that is a workspace. It's a robot workspace. So for you, it's Catkin _workspace. So are you in your Catkin _workspace directory? And then you can see what's there. There's build, demo, and SRC. These are the classic folders in a ROS structure. So get to your Catkin workspace directly, not to Turtlebot. Turtlebot I have created for myself. So get to Catkin workspace, and in my case it's Turtlebot workspace, and make sure that you see Catkin_workspace here. Now this command, I do it each and every time because it's like setting up your environment. You know, when you work on different projects, let's say you're an accountant and you're working on client A, client B, client 3, right? After you finish with client B for the day, you put everything in a file and you put it there, and then you bring client A here. So that's the effect of this command. It's saying that I'm working on a certain environment. That's the whole purpose of this. It's like the project you want to work on right now. Then you'll close it up and you'll open up a different project. There is an alternative. There is something known as a bash file. I don't know whether in your ROS2 session you are exposed to that. So you can put this in the bash file. But you know what the problem with putting this in the bash file? Every time you open a new terminal, the bash file runs. So that means if you're working on a different project, now you've gone too far, right? Because you have to edit the bash file and remove that command. So it's a little bit inconvenient to put this command into the bash file. Some people do it. You know, if they only have one project, they put it in there. I don't. It's possible to work with ROS Melodic, the older version. So better not to put those things into the bash file if you are going to work with different ROS versions. Then there's ROS1 and ROS2. You can have ROS1, you can work on ROS1 projects as well as ROS2 projects. So you've got to have all this separated by these commands. Otherwise you'll be mixing stuff. It'll go to the wrong directory. It'll think you're working with ROS2. So I run the source command. Did you run it?
Yes.
Okay, now I have this command. I've run it so many times that it's there in the past. See, you can in Ubuntu you can cycle through the previous commands. So use the up arrow, and that looks like it. ROS launch, Turtlebot 3 gazebo. Now if you don't have it, you copy it. I'll wait for you because you haven't worked yet on this system. So this launches an empty world. Turtlebot 3 in an empty world. That's what it is. Let me read it out for you. ROS launch. Space. And by the way, there is something known as tab completion. So I'm sure it is there in ROS2 also. When you type part of a word and then you hit tab, right? If there is only one choice for the completion, it will immediately give it to you. If not, if you double tab, it will give you all the options. Then you type a few more characters and then tab again. And therefore you avoid typos. You really don't want to type out, you know, because human beings are not very good typists. So when you use a tab command, you will know that, you know, what are the options available for this. So I want you to run this ROS launch, Turtlebot 3 under gazebo. If you're wondering what is this, you know, what is this and what is that? This is the package. So this is the command, this is the package, and this is a specific launch file within the package. There can be many launch files in the package. So command, package, the launch file within the package. It happens to be the Turtlebot 3 in a completely empty world. We don't want any obstacles right now. So this might take a little bit longer on your machine. So remember I told you Ubuntu and ROS are multitasking systems. Do not kill this window. This is a window that's running gazebo. So don't type in it or you know. So you know how we're going to interrupt the program? We're going to say come back here and then we're going to hit a Control-C. This window is in charge of that process. So don't try to close it. It is supposed to be alive till you're ready to go home for the day and kill gazebo. So basically you can minimize it and forget about it. And it's here at the side. See? Gazebo. So there's the Turtlebot. It looks much prettier when you look at it on a regular screen. Here it's kind of fuzzy. Is that okay? And you can pull down obstacles if you want. To position it, once you've dropped it, you got to go to this. This is a positioning tool. See here, translation mode. Here. There it is. I want to move it here. Because when I run the program, the robot is going to take off this way. So I don't want to have it hit this. You can also rotate it, but rotating a cylinder is not going to make a change. You can resize some of them, not all. Now this is too tall compared to the robot, which I don't like. So because I can't see the robot otherwise. So just try and do that. Now in the folder on Teams, I have posted a picture of a 3-button mouse. You cannot do any robotics work with the trackpad. Well, maybe you can figure it out, but it's not easy. So you definitely need a 3-button mouse. Pretty fancy, eh? I bought it in December because my old one stopped working. So I'll pause just to make sure that you're able to move the cylindrical obstacle here. This one rotates, that one translates, that's just to select. And this one sizes when it's possible. Typically only for symmetrical objects you'll be able to size it. Meanwhile, get your MATLAB ready, launch MATLAB. I'll show you my MATLAB screen. It looks like any other MATLAB screen, no mystery. But I'll show it to you anyway. Increase the height. So you have to go here. And then these are the handles. I'm going to try something. Maybe I'll regret it, but I want to show you a little bit more. So over here, that opens a new terminal because you can't use the other terminal. It's locked down. It's married to the zero. So over there you can open another terminal. Notice it will drop you in your home directory automatically. And then you run ROS run, or you run the command ROS run. Notice the tab completion. Always. So the tab completion actually confirms that your environment is set up. So I often use that. If the tab completion is not working, it means you haven't sourced devel setup.bash. You haven't run that previous command. So that's a good test to see whether you have created the environment properly. So has everyone got this command popping up automatically on tab completion? ROS run, space, just hit RV and then tab completion. Space, RV and tab completion. You can even hit ROS. Okay, let's try that, but yeah, I can try that. Maybe there are too many completions possible. Yes, see, it doesn't respond. And these are all the possibilities. So I go one more, R. And maybe that will reduce the number of possibilities, yes. You know what tab completion is? Hit the tab key. So, no space. Is everyone here? Okay, I'm running it now. And again, that window is tied up. Don't touch it. That window is tied up because it's running this process. See, that is the beauty of Ubuntu. You can run multiple processes in parallel. Okay? No underscore. ROS run space, Orvis space, Orvis. All lowercase. I'm going to do something that sometimes causes a crash, but I'm going to try it anyway. So I don't like this dark background because even if I put a robot there, I won't be able to see it. I haven't added a robot yet. I'll get to that. But I try to change. See, there is a little. If you go somewhere here, you'll see that you can change the color. All right, so I'm going to show you how to launch ROS. Because some of you are just at that phase. So let me go to that terminal. So that's the terminal. I've already run it. That's why I had to go back and look at the command. So you run, you type ROS run with tab completion if you want, space ROS, space ROS. That's basically robot visualizer. That's ROS.
So ROS is not installed, like ROS is not installed in my PC.
And if I try to use ROS patch install, it's not getting installed.
You don't have ROS available?
No, ROS run is not found. ROS run package.
Oh, you don't have a ROS run.
Yeah.
Then just run it as ROS, but then you'll have the problem that the frame transformation is missing.
Try that. Just type ROS and
Type ROS, but I think you'll get some errors. Just run ROS by itself. How come theirs is working?
Sir, after that, we just need to try and run with the ROS directly.
You can run ROS directly, but it might be missing some things. So let's see what you get.
Those who don't have ROS, you can install it. Sudo apt install ROS.
So I'll tell you what, we'll get back to ROS later. Let's skip the ROS part and just go to the MATLAB program, and then we can come back. So ROS needs to be installed. So let's skip the ROS. So I'm going to shut down ROS. Can I at least show it to you?
Yeah.
So that when you install it, you can try it, because remember, the roadmap is there. You just have to follow the roadmap, right? The whole script is already uploaded. Okay, so let me show you what ROS can do. So as I was saying, I don't like this coloring scheme, and I tried to change it, and let's pick something that is light. Maybe this.
See, what's the problem?
No, let's forget the ROS. Let's forget the ROS for now. Yeah.
They are doing another terminal, that's because if you open the ROS noisy terminal, in there itself you can add another filter. But if you go for the new terminal, in that there is no ROS, no receive.
Yeah.
That's the problem.
Is that fixable in 2 minutes or no?
After 2 minutes.
Yeah. So Ubuntu is very complicated. It takes a lot of learning. I'm not an Ubuntu expert. For example, I'll show you here. Who understands all these messages? Well, obviously the people who live and die in Ubuntu do. So OpenGL device, LLVM pipe, and some numbers, right? So you have to get to a level of comfort with using it as a tool. If you get involved in learning Ubuntu, you'll be spending the rest of your lives on it. So at some point, with enough practice, you'll have the confidence that you don't need to go down deep. Life is very complicated. You cannot know everything in as much detail as the experts know it, because it's humanly impossible. So the Google search box often helps. If you get an error, you cut and paste it, and you'll find a solution. That's how I do it. Okay, so I'm going to add the robot, right? Now, by the way, it's saying fixed frame, unknown frame map. So you have to have one fixed frame of reference. And right now it's defaulting to a map, right? It says use the frame used by the map, but no map has been loaded. It defaults to it. So it's looking for the map, and it says you don't have a map, but you're making me use the frame in the map How is that possible? There's no map. So that's the first thing you need to do is you need to replace it by ODOM. And on Saturday I'll tell you what ODOM frame is. So the error goes away, right? So go up there and change the fixed frame to ODOM. There are other fixed frame possible. You can actually make the wheel as the fixed frame. That will be pretty odd, right? One robot's wheel axis, in ROS there are multiple frames because things are rotating, you have to assign a frame to it. If you have a camera that's pivoting like this, it has to have its own frame. Otherwise, how will you relate all the pieces of information, right? If you have 5 cameras, you have 5 frames. If you have 20 robots, each with 5 cameras, now you got 100 frames. That's why ROS is so complicated. It helps the human being, manage things. Because otherwise you will not be able to handle this, like 100 frames. No human being can do that. Okay, so ODOM. And then I'm going to add a robot. So, unfortunately, with this resolution, I don't get the bottom here. So I don't remember. Let's see, this morning I was able to figure out a way around it. There it is. If I show the help panel, it pushes the add button up here. Now you're not going to have the problem with your own computers. Okay? So please get the image and load it on your own computers. I'm getting this because the resolution on the screen is pretty miserable. Add. See, I told you Orbis is a spy, right? So it's got all this information in it. All kinds of things. So first thing I'm going to do is add the robot. Here it is. So the robot model is added, there it is. And again, you can use the 3-button mouse to zoom in and all that. Now one thing you're going to find is the functions of the mouse might be slightly different in Orbis than Gazebo. Don't ask me why. This is the open source community. They do things the way they want. And you can't question them because you're not paying them anything for the service. So they will yell at you. So you can zoom in. Another thing you'll find is the gazebo view of the robot is different from this. You're going to have to turn this around to align it with a... Why is that? Don't ask me. It's an open source community. So you have to turn this field around to make it align with that. Okay, now we're going to add the LiDAR because the TurtleBot has a LiDAR. It's a 360-degree LiDAR. So I'm going to add that. And after doing all this is in the roadmap. We don't have to memorize anything. Oh, it's not showing up here. Oh, it's somewhere here. I'm not able to get a pull down menu here. Hey, can you change the resolution and make it so that I can see what's going on here? So, I'm not able to pull down this. This way. Oh yeah, that's enough. Topic. Remember topics?
Yeah.
And publishing? So you need scan. You saw that? You see this? It just popped up. So do you realize the alignment is not quite right between gazebo and Orbis? It is showing you the LiDAR rays are hitting the cylinder. No? You don't see that? I'm going to increase the size of the points to maybe 3 times. Can you see it now? Okay, here. So do you see what's going on? Does everyone see what's going on? The robot is able to see the obstacle. Which obstacle? This one. It's slightly misaligned. I told you, ROS and gazebo are misaligned. We can change it. Why does it not see the entire base of the cylinder? It's not a base, by the way. If the LiDAR is mounted here, it's only going to hit obstacles at this height. So if there's a young child who's not as tall as the LiDAR mounting, the robot is going to run over the child. This is a two-dimensional LiDAR. This is a two-dimensional LiDAR. A 3D LiDAR will see everything. This is a 2D LiDAR. 360 degrees, one ray per degree. So 360 rays. Is that okay? 360 rays. All of this is the roadmap. Now let's get to the main part, and then we can double back if we have time. So I'm going to minimize it. And bring back the MATLAB program. So I'm going to,
We are getting error for robot laser scan and robot model.
for the ROS, right?
Yeah.
Forget ROS. Close it down and you can do it later. Yeah.
Okay. So ROS you can close and
Yeah, close the ROS, leave the gazebo open.
keep gazebo open and open with MATLAB.
Yeah, MATLAB and gazebo. So all MATLAB programs will have this structure. Any program you write will have most of the structural aspects that I'm showing you here in this program. So you can use this as your sample program to build anything. So at the beginning, MATLAB is an interactive environment. So in fact, as you're running it, you can put a pause, you can look at the variables that are piled up, and you can change individual variables to see whether your algorithm will work. So maybe you got an intermediate result that is not correct, right? But you don't have to panic and say, okay, let me go back and look at the whole program. You can say, okay, I'm going to change the variable to the correct value and see whether the rest of the program is working. That is the beauty of MATLAB. You can't do that in C++. You can only do it in Python and MATLAB. So because of that, every time you run a program, it leaves all the old variables here. So maybe you said, okay, enough for this, I'm going to a different course. And you run that program. If there is any conflict, it's going to use the variables in the workspace. So that's why at the beginning of each program, you insert this. Clear variables, close all. If there are files that are open, it will close it, and CLC clears the screen, I believe. So this is like, your basic starting, thing. It's like saying a prayer at the beginning, in the morning, something like that. You always insert that. Now this ROS shutdown is needed because typically robot programs are in an eternal loop. It's like you're saying, run the robot around this building until I tell you to stop. So that means it's eternal, right? And the only way, it doesn't have a normal exit. The only way you can interrupt the program and stop it, in other words, is hit a Control C. So if you hit a Control C, ROS will not have shut down. And then next time you run it, it will say, ROS is still open, why are you asking me to run ROS core again? So therefore, the shutdown is in two places. It's here, and it is at the bottom of the program also. It doesn't matter if you shut down ROS twice. It's just going to say it's already shut down, right? So when will this shutdown be reached? When it's a normal exit. That means the mission is complete. You have reached the goal. But most robot programs go on forever, and you'll need a Control C. Gazebo, you'll have to do a Control C. There's no other way of interrupting it. It's running right now. And in my case, ROS is also running. And maybe you can have 15 windows that are running. If you have a very complicated problem, you'll have to shut them all down at the end with a Control C. Is that okay? So Ubuntu is like a live piece of software. Multiple things are going on. Okay, back up again. Yeah, we have time to do this. So this is very important because IP, the way you communicate is using the TCP/IP protocol. right? Now, in my case, I have set it up so that there is a static IP address. That means if I close my computer and go home and I open it, I don't have to change this line because the same IP address would work. In some setups based on the networking mode, you have what is known as a dynamic address, which means that the address will change. So how do you deal with that? What you have to do is, you have to open up a terminal window. See, all of these are occupied, so you have to open a new one. And then you type ifconfig. Is that okay? That means you're getting the IP address. See, mine never changes. So if you don't do that, the MATLAB will not connect to ROS and Gazebo. So if you log out and come back, or even shut the lid and go home without turning off the computer, or even if you turn off the computer, you'll have to get the new IP address. Is that okay? So if your MATLAB program does not run, it means the connectivity is lost. This is based on the TCP/IP architecture. So you can just, I like to write a lot of comments in my program. They are like novels sometimes. My programs are like novels. Okay, here is another block. Now here's where you set up the publishers. Now remember, you have a robot, right? You want to drive it. So in ROS Noetic, the topic for driving it happens to be command_well. Just like this. You just copy it because you have the program. And the message structure is also needed. This is the data structure for the messages. And then I give it 2 seconds to kind of complete itself. Then I create 2 subscribers. Don't worry about model state. Should be model. Don't worry about model state. I'll tell you on Saturday what it is. ODOM is what we are interested in. So what is ODOM? So if I measure the rotation of the 2 drive wheels, you'll see on Saturday it is possible to figure out where the robot has moved. That's known as odometry. So if I can count the number of rotations or partial rotations of the wheels, I can predict where this differentially steered robot will end up. So that's what ODOM, standing for odometry, is. And that you subscribe to. This one you publish to. So 1 publisher and 1 subscriber, because we're going to ignore this model state for now. And then having created the publishing, so this just creates a publishing object, right? And then I create an instance of it, sub-ODOM. This name can be anything you want. On the right, it cannot be anything you want. It's locked down. On the left, it's whatever variable you prefer. So ROS subscriber ODOM, and then you create an instance of that. Similarly, you create an instance of the publisher. So these parts you just blindly repeat. Now what am I going to do with pub/well? So that pub/well is a structure, right? Pub/well is a structure that obeys this message structure. And I'm going to push my velocities into it. How exactly? This way. So I get an instance of the object pub/well, and then I'm going to define my velocities. 0.4 meters per second, 0.2 radians per second. And remember, the ratio is 2 meters, right? So if this works, the robot should move in a 2 meter radius circle or 4 meter diameter circle. So I'll be jumping back and forth. So here, see here, VEL message.linear.x. Now how did I know that VEL MSG has this kind of a tail or 2 tails? I'll tell you in a second. I have to run the program. All the variables will show up here, and I'll show you how I unpacked it to know which part of it is velocity forward and which is rotation rate. And remember, I have defined numbers for this right here. Do not put 0.4, 0.2 here. So that's known as programming using magic numbers, because when you look at the program after 6 months, you'll wonder, where did these come from? So if you want to understand your own programs, then you have to comment like I have done. I leave lines between them so that there's readability. So I have defined the velocities here. I could have just avoided that by directly putting in the numbers here, 0.4, 0.2, but then you won't know what it is those are. And now I'm ready to get the ODOM data. I'm going to plot the path of the robot. So I want my first point. So I say receive. So that gives me the latest odometry point. So receive gives me the latest, the last odometry point. The robot is not moving, right? So I'll get its initial location. Don't worry about model state. And then I deconstruct the ODOM data into my local MATLAB variables. Now you don't have to do that. You can use ODOM.pose. I'm getting tired. I don't like carrying these long structure variables through my code because every time you write a line of code, it wraps over multiple times or it becomes so long that you can't see it. You have to sort of, shift right and shift left to see the whole thing. So these days there's so much memory in the computer, you can use additional memory for clarity. It's worthwhile using memory for clarity. So I unpack them using the MATLAB function deal into X and Y. Number one is X, number two is Y. I'll show you why. I'll show you how I got that. I did not just guess it. So then I put it in X and Y. Having obtained it this way, I then shove it into X and Y, which is more recognizable. You don't have to. You can use ODOM pose 1 and 2. I'm a very careful programmer. I waste memory because I like clarity. Okay, then comes the loop. Now, this ROS rate object is something that enables you to measure time within ROS. So here what I'm saying is ROS rate 10 is R. So I create a rate object, which means that I want time. There's going to be a loop. There's going to be a loop. How else will you drive the robot? Because you've got to say drive, and bring it all the way around till it has finished a circumference and then say stop, right? How else are you going to do that unless you do a while loop of some kind? So, there is a while loop down here. See? While. And how I'm driving it is as follows. I know the forward velocity, right? I know the radius of the circle. Therefore, I know the circumference of the circle, right? So if I want to drive a full circle, if I know the circumference of the circle and the velocity, I can get the time it takes for it to complete a circle, right? And so this loop is set up to drive as long as it takes for the robot to travel a full circumference. How did I get that? Let's look over here. Radius, velocity by rotational rate, right? Remember V by omega? Circumference, 2 pi r, right? We recognize this from back in high school. Time for robot to complete one circle, circumference by velocity, is that okay? And thus, I'm checking while, see the robot travel time has been initialized to 0. It will be updated somewhere within this loop. So right now it will start with 0, it will say true. 0 is less than TC, it will start to do the loop. Is that okay? But over here, I've got to update the time. And that's where the rate object helps, because the rate object has something called total elapsed time. So R dot total elapsed time will give me the amount of time that has elapsed. And I take that number and park it in RTT. And it will be updated. Every time the loop goes through, it will be updated. And then I say move. I tell the robot move. So I publish, send pub-well. Remember, well message was packed with the velocity information. And then I say send it to the pub-well, because that connects to the robot's drive system. Now, one thing you're going to find out here, maybe for the first time, you've got to tell the robot to drive. You know why? You know the system we have with our trains, with the people who drive, the engineers? If they have a heart attack, you don't want the train to go on forever. So basically, if they release that lever, we assume that if they have a heart attack, they're going to fall backward or something. Then the train will come to a stop. That's true for every robot in the world that is a commercial product. Is that clear? You have to have that safety. In other words, if it doesn't see the next command, it assumes that it's time to shut down. That is how they do assembly lines, manufacturing places, that if there's no attention, it will stop on its own. Either the attention has to come from a program or it has to come from a human being. In the case of an engine driver, it is a human being. Here, if the program doesn't keep telling the robot to move, it's going to stop in order not to hit somebody. So, that's why this is in the loop. It says drive, 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 keep on driving, basically. So now it's time to update the odometry, right? Because the robot is moving. I have to get new points. So I do the same thing that I did outside the loop. Go down, receive, remember that? Yeah, here. So you do it within the loop. Receive, sub or down, and then unpack it. And so this is, MATLAB has this ability to augment. So the old X and Y is augmented with a new value. MATLAB doesn't like this because anytime you create an array by adding to it and making it longer, it's a slow process. So that's why you get a warning. It says don't do this. See right here? But I ignore it because this is clearer to me. The way to avoid it is by pre-allocating a long array. So you say how many points will I have, right? And then you pre-allocate and then you don't have to augment. But I prefer it this way. And then this is something unique. We have the time, so I'm going to jump into it. So what this does is, in robotics, you're not supposed to run a loop faster than is necessary. If you're driving a mechanical system, is there any point in saying drive at a rate of 10,000 times a second? Because the system is incapable. It's a slow. All mechanical systems are much slower than electronic, devices and computer programs. So there's no point in saying drive, 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 drive. Because it's not. It can't even get to your next command because it is so slow, right? So therefore, what are you doing when you let the while loop run at infinite speed? You're not giving yourself the ability to take some time and allocate it to other nodes. Because remember, in ROS, you're going to be running multiple nodes. Not in this program. This program is very simple. But you may have 10, 15 nodes. So if every loop is being run at blazing speed, you're actually not using the computer's resources properly or efficiently. That's why each loop has to be run at a certain rate. So if you have an image processing loop, images come in typically at 50 frames a second. There is no point in running it any faster because cameras are incapable of producing images faster than that. So typically you allocate these rates to different processes. That's like a surgeon. You have to have some knowledge to be able to do that. But what I'm doing here is, I'm saying, slow down computer, don't sweat it because you can go at what rate? I didn't tell you that, but this 10 means 10 times a second. That's enough for the TurtleBot 3. 10 is 10 hertz. Right? What is the reciprocal of 10? 100 milliseconds. So every 100 milliseconds I'm giving it a command. Even if I go faster, nothing is going to be different. You get the point? There's no point in going faster. So this is something that you need to do in robotics. So I try to create a habit here. But also remember, we're also using the fact that it's giving me the ability to read time here. So I update RTT. And so when it's finished, see I'm burning the rest of the time. Burn the rest of the loop time. Burn means not computer stop and go to bed. That time is actually available to other processes if you have other processes. Okay, stop the robot. I pack 0, 0, got it? 0V, 0W, omega, and then I send it again. And then I do all the plotting here. So in this program, the mission is complete, so ROS can be shut down here. Now, hopefully it'll run. I've got to line up, gazebo's here, so I can quickly click here. Let me run it, and come down here. Oh, I didn't expect this to be here. It's moving, right? Is that 2 meters? Can you see that? Every floor tile is 1 meter by 1 meter. And see 4 meters right there, approximately. And then it will top out at -2 there. Now it's going to be off a little. I'll tell you why. Let's watch it. You see the stop what it did? So in gazebo, they try to program the physics of the robot in. So that kind of a turn, when you stop it, it's because they've attempted to program a real world effect. So it's kind of skidding this way. Now you're saying, why is it skidding this way? Is one of the tires, more bald than the other? We don't know how they programmed it, but all robots that are modeled realistically should have something like that. Not only that, if I run it again, it might not do the same circle. And that's good, because in the real world, if I run a robot, now let me give you this example. I blindfold you, right? And I ask you to take 100 steps in this direction. First of all, you can't go straight. You will not be able to go straight. No human being can go, unless you look up. So I blindfold you, I say 100 steps, come back, do it again. You will end up in multiple places. Same thing with robots. You cannot precisely repeat an action in the real world because there's too much uncertainty. The grip is different the next time, right? Maybe you're tired and your steps are slightly, shorter, right? Not you, but the robot can stumble, right? If the robot hits a stone, the right wheel will come up, it will spin, right? But the left wheel is on the ground, so you'll get a rotation, won't you? If one wheel is off the air and the other wheel is on the ground, you'll get a rotation. So each path is different from the previous path, and so they make an attempt to make the simulator realistic. Okay, now let's see if I can show something with ROS. Okay, it's back to its original position. Now, one thing you'll notice is that there is a button here which says reset model poses or reset world. Let's try reset world, also resets the model poses. Just watch it, okay? See? Remember I moved the cylinder, so it puts it back to the original place. Now, this is okay, isn't it? Because it's not going to, no, that's going to hit the robot. Let's move it, because 2 meters would actually cause the robot to hit. So what I'm going to do is, I'm going to move it a little bit inside. And then I'm going to go run the MATLAB program, and we're going to go look at ROS if I can do all that. So here, what happened? Oh, okay. Where is ROS? You see this? Oh, don't do that. It is going to go off frame. So why is that? Because the LiDAR is only catching one side of it, right? Oh. Isn't that beautiful? Are you getting emotional? When I was younger, I used to, but then I became, more serious. So it's oh, I didn't show you the plot. So that's the plot. Notice, it doesn't quite close. You know why? So, for that to close, you have to have a closed loop control system. So for a closed loop control system, you have to monitor the target variable. What is the target variable? It should really be distance, not time, right? What we are saying is, I have a circumference of a circle, I divide the circumference by the average velocity, but wait a minute, it's not average velocity, because the robot is starting from 0. So when I command it to go at 0.2 meters a second, is it immediately going to reach that speed? No way. So monitoring time is not enough to monitor distance. It's like you're driving home and you say, I'm going to drive for 15 minutes, I'll be home. No, it depends on the velocity and the traffic conditions, right? So you should really be monitoring velocity. This is what is known as an open loop system. And therefore, you get this little gap here. See, it hasn't quite made it. To the eye, it looks as if it has, right? But when you plot it, you see it's a little bit short. And I know ROS is not working, and that's because the package is not downloaded. But ROS, this is the usefulness of ROS. You can debug problems because it will show you the LiDAR view, it will show you all kinds of things. I did not turn on the odometry. I plotted in MATLAB, but odometry is available here. Oh, by the way, yeah, let's do this. Because I said, how did I get to know that odom, contains, is structured this way? Well, see, all the variables here are here. Once you run it once, those variables show up there. So let's see how to find out where all the useful information is. Oh, no, I'm sorry, I should have clicked on that. Hold on. So we're looking for something called pose. So pose is a term for the position of the robot. Position doesn't just mean X, doesn't mean Y. It means X, Y, and orientation. So there are 3 numbers. Because the robot is forced to move on a plane. If the robot were to be a drone, then how many numbers would you have? You would have 6 numbers. So a body that's in space has 6 degrees of freedom, right? So here, because it's moving on a plane, there's only 3, X, Y, and theta. So here it is, the pose. Double click on that, and you go, forget the go variant for now, and position, got it? And there's your X, Y, and Z. So the Z is not going to change because the robot is on a flat plane. But that's how we find out. Look at this. There it is. So that's how I figured out that that's the variable you want. So it's not me being brainy. I just looked it up. Is it okay? So that's how you unpack these structures. Initially, they're a mystery, and then you figure it out. And is there anything else? The velocity message. Here. So linear is like forward. So right now, they are all 0, right? Because the robot is stopped. But when it was moving, I could have monitored this, and plotted the velocity. And then you would have realized that there was an initial acceleration. That it was initially 0, and then it had to accelerate to get to 0.2 meters per second. So let me tell you something about model state. I know we are almost, time's almost up. So model state is something that is the true state of the robot. So how can I get the true state of the robot? Well, you can't in the real world. In the real world, you cannot get the true state of anything. So if I asked you, what is your height? You'll give me a number, and in your mind it is precise. Not really. If I measure that again, maybe the next day you're a little bit tired and you're like this instead of like this. So the point is, anything in the real world, right, is not 100% accurate, right? But this is a simulator. Certainly the people who wrote the software know where the actual robot is, right? What we plotted was based on odometry, the spinning of the wheels. But the true location of the robot is known. So in any simulator, they have something known as model state. So if you are plotting an odometry and you want to see how accurate is my odometry, did the robot hit a stone, right? That caused its wheels to jump up. You can compare with model state. That will give you the true location of the robot. It's only available in a simulator. In the real world, how do you manage? Let's say that you're trying to write a program to localize the robot accurately. So what you have to do is, you have to find a form of measurement that is more accurate than the method you're trying to test. And that becomes your model state. Everything is relative, right? So you have to find some other means that, for all practical purposes, can be considered to be the truth. That's how you operate in the real world. In the simulator, you always have model state available to you. So GPS readings, if you take it multiple times, it'll say you're here, you're here, you're here. Obviously, you can't be at all those places at the same time. And that's because any real world measurement does not have 100% accuracy. It just doesn't. And yet we're okay with that, right? We're surviving. You don't need 100% accuracy. You only need the accuracy for that particular application. When you launch a rocket, the demands are much higher, right? When you're trying to get a robot to go through a minefield, obviously you have to locate yourself precisely, right? Because you don't want to run over a bomb. So everything is relative. If a robot is running next to a swimming pool and it is not waterproof, yeah, you want a certain kind of accuracy. Me walking down the corridor, I don't need that kind of accuracy, right? If I go a little bit to the right of the hallway or to the left, it's okay, nothing is going to happen. Now, same thing with driving a car in a lane line, right? Nobody drives down the middle of the lane line, by the way. You always drift a little bit, and by the way, Chennai, they drift all over the place. So, the point is that perfect accuracy is not needed in the real world. So, I'll see you on Saturday. Hopefully, you would have installed the software in your own computers, because then you'll have a much better experience. Those of you who could not keep up because of software issues, I have posted the roadmap And so you should try to cycle through it. The only thing different is you'll have to set up your own IP address. So I'll see you on